Welcome back, everybody. Today we're going to talk about a couple of special case triangles. We have one which is a 30, 60, 90 triangle, and another which is we call it a 45, 45, 90 triangle. Both of these have some unique relationships between the sides, and we're going to look at those with a couple of examples. We'll work through a couple of problems, and for each of them go over just really basic and simple proofs of how these work. So with that said, we're going to go ahead and get started. So what we have on our screen here, I've got the Deathly Hallows symbol. You maybe have seen this from Harry Potter, right? This is the emblem that Xenophilius Lovegood wears. This is the exact copy, obviously. It's not an image. It's not a drawn image. It looks exactly like it in the movies if you watch those. Obviously, I'm kidding, but that's okay. And so in this, we have some really basic information. We're looking at a very unique type of triangle. In fact, this one is a special case triangle, an equiangular triangle, which, as we know, means that the sides are also going to be the same. They're going to be uniquely the same, and that's going to be helpful for us. So that means if this is, sorry about that, if this is given as a length, we could say, I don't know, we could say it's 3 inches. So we'll draw that here, 3 inches, which means that this side overall would also be 3 inches. And this side, again, kind of repetitious, but that's okay, would also be 3 inches. When we look at that, that tells us a bit of information that's useful. Now, one thing that we need to understand here, I'm going to go ahead and draw another triangle here. And we'll go ahead and say that's a triangle, make it a little more, there we go, that'll work. And we're good. So then what we're going to do is we're going to just draw this piece here. We're saying that's a right angle. This actually is what we call, so these angles are all the same, this is a perpendicular bisector. So it's creating two smaller halves, also cutting the angle in half, making that 30, 60, and our 90. If we said that this side length was 3, that means that this side length here would be 1.5. So our relationship, we're saying, is that this side right here is 1/2 of that side. And hopefully that's fairly obvious to you. We already know that this would also be 3 inches. We could then use the Pythagorean theorem to solve this. And that's okay, we can go ahead and do that, but I'm going to go ahead and skip that for now and just show a general proof for this. So I'm going to draw another triangle without any numbers to it. We'll just go ahead and do another one here. I have our triangle now, and what I want to do is just give it some basic information. We're going to call this B. This hypotenuse, if you will, is going to be B, which means this would be B over 2, and we're going to say this is just height. We don't know it yet, but that's okay, we can solve for it. In our Pythagorean theorem, we know we have a squared plus b squared equals c squared. So let's plug in what we have. Our c squared we're calling just b. Our b squared we'll call b over 2. We would square this whole thing. And our h, there we go. Our h, again, is just going to be h squared, whatever that is. For now, when we go and plug these in, we're going to go ahead and, sorry about that, there we go. We're going to go ahead and solve for h by taking h squared and setting it equal to b squared minus, we're going to say it's b over 2 quantity squared. The reason, again, I'm not worrying so much about the squared terms is because we're going to go ahead and change all that here in a second. So we take b squared, and again, I'm just going to say h squared equals b squared minus this whole piece right here, this section and this section here that we've got squared. We're going to do the whole thing, which ends up being b squared over 2 squared, because we square this across to both terms in here. So when we do that, we end up getting h squared equals b squared minus b squared over 4. So essentially we have this is 4/4 or a whole one, and this is 1/4. We have 4/4 or b squared, that would be the same thing. We're going to go ahead and draw that in here. Let's just go ahead and draw that equals 4b squared over 4 minus 1b squared over 4, because that's what that is. And that gives us h squared equals 3/4 b squared. So now what we want to do is take the square root of both of these, which we're going to do. And that's going to give us, on the left side, just h. And then the right side, we're going to get square root of 3 times b over 2. And that's kind of a neat little trick, but let's check the numbers on that to make sure that it works. So now we have this answer, but what does that answer mean? What does this mean? What does that mean for us? Well, it means that this height is being multiplied a radical 3 or square root of 3 times the original b over 2. So we know that the relationship here is that this is 2 times to get to there, or this is 1/2 to get to here. The hypotenuse is double the length of the short side, and the short side is half of the length of the hypotenuse. And that's pretty straightforward. The height, this piece here, this altitude drawn, happens to be radical 3 times the short side here. So that's really all it is radical 3 times that short side. I know it's hard to see past that trial here. We'll go ahead and edit this a little bit and move it up so we can see it. So we now have our math on here that says, easy enough. What we want to do is apply that to our original equation. So we're going to do that now. So in our calculator, we're going to go ahead and plug that same thing in. Our original equation, we could go the Pythagorean theorem route and say 3 squared minus 1.5 squared equals our height once we take the square root of that. But what we're going to do is just take 1.5 and we're going to multiply that by the square root of 3, 2.59. Just to confirm that we did that right, let's take our hypotenuse to the power of 2 minus the 1.5 to the power of 2 and enter, and we're going to take the square root of that, and we're good. So this is a simple proof for the 30, 60, 90 triangle. Let's move on to the next one, which is the 45, 45. But before we do, let's go ahead and just have some information here so we can view that. It says 30, 60, 90 triangle. This one is set up to show, again, that the long leg is only a square root 3 or a radical 3 times the short leg, and that the hypotenuse is twice that of our short leg or our short side of the triangle. All right, so moving on to the next one. I have a clock here. Maybe it's a clock we're familiar with. I believe we call that Big Ben. I went and just sketched out a really simple version of it, and that would mean that this is, always got to change my layers here. That would mean that this would be Westminster Bridge, right? Now, I know there's a bit of a building showing up in this area here that would block and obscure some of our view here. That's okay. So we've got Big Ben. It's roughly 96 meters, or about 315 feet, I believe. So 96 meters tall. We've gone and sketched out another line here at 96 meters out. We have what we call a 45, 45, 90 triangle, because this is, in fact, there's another name for it, isosceles triangle. What that means, if you remember an isosceles triangle, that the sides and angles that are opposite them are the same. We have a 90, 45, 45, 45, 45, 90. However you want to write it in order, we have an isosceles triangle. And so we know that these lengths are 96 meters. We know that the angles are 45 meters. If we were to go draw another triangle here, and say that same information 45, 45, 90, then this would be a length, some known length x. This would also be a length x, and this would be our hypotenuse. Let's go ahead and do another little proof for this. Since we're all about these proofs right now, we would take a side squared plus the other side squared equals our hypotenuse squared, or a squared plus b squared equals c squared. Notice these are the same. So we can actually write that as 2x squared equals h squared. So to solve for our hypotenuse, we're just going to square root both sides. And that gives us the square root of 2 times x equals h. Notice, this is only a step up from the length of the side by a radical 2. So that means in a 45, 45, 90 triangle, we can simply take the square root of 2 times either of the side lengths, since they're the same, and multiply it together and get the hypotenuse. We take now any really triangle we want. We'll go ahead and just make one here and make it look clean. Let's go ahead and edit it a little bit so it looks more like a 45, 45. There we go, perfect. So now what we're going to do is mark it up, 45, 45. If this measure of the length on the side is 3, then we know that this is going to be radical 2 times 3. And we're good to go. Conversely, or I guess going back the other way, if we said this was radical 3, then we'd know that this would be radical 3 divided by radical 3, which ends up just equaling 1. Because again, we multiplied to get to the radical 3, we divide by radical 3 to get back. So we're going to go through a couple of examples, but real quick, let's go ahead and just make sure we've got something for our notes. I'll shift there, but so we have our notes here. In the notes it says, just to summarize again, in a 45, 45, 90 triangle, the hypotenuse is radical 2, or the square root of 2 times the length of either of the legs. Again, both legs are the same. It doesn't matter here. So we have hypotenuse is equal to the leg times a radical 2. So now let's go into an example. We have 2 dump trucks. Well, we have 1 dump truck at different points in time. We have the one on the left, which is our 45, 45, 90 triangle, and the one on the right, which technically only shows us a 90-degree angle and a 60-degree angle, but we know because of the angle-angle postulate that the other angle, the angle sitting right up here, is 30. So now what are we going to do? Well, let's go ahead and run both of these as separate examples. On the 45, 45, 90 triangle, we know that in this example we're given, you know what, I want a better version of that. And I love to be able to edit these, super fun. So now we have our 45, 45, 90. We have some information here. 14 feet. And we want to know what is this and what is this. Technically speaking, we only need one of those. So we know to get from the unknown length, we'll call this x, we multiply by a radical 2 to get to 14. So to get back, we just have to divide by a radical 2. And that gives us x equals 14 over the square root of 2. So in our calculator, we'll take 14 divided by the square root of 2. And our calculator will do all that for us. If we were leaving this into rationalized numbers, we'd have just 14 over square root of 2. We'd rationalize the denominator and get 7 roots of 2, but we're not going to worry about that. We'd get 9.89 to the nearest tenth, 9.9 feet, approximately. if we want to go ahead and check and do that as a rationalize the denominator again, if we were going to do that, we would multiply both the top and the bottom by this. Those end up giving us 2 in the bottom, 14 still here, and we have a radical 2. That crosses out to be 7, or 7 roots of 2, if you're looking for a rationalized denominator method where we don't use decimals. But again, in the real world, no one thinks in radical numbers. Normally, we think in decimals or whole numbers, maybe fractions. On the right side, same setup, but now we have a triangle. Let's go ahead and adjust this just a little bit so it looks a little better. Perfect. We know that this is a 60 degree because it's given to us. We know that this is 30. So we know that this is our shortest side, and we know this is our longest side. Well, if the hypotenuse is 14, we know the short leg is going to be equal to half of that, so 7. The long leg is going to be equal to a radical 3 times that the shortest leg, which is 7. So in better terms, we'll write it like this. And that would work for us. Easy enough. There's not a whole lot of manipulation of data because going from the hypotenuse down, super simple. If we had been given a number for this length, we know that we would have to divide by a radical 3 to get back to here. So if this was square root 3, as another example, I guess, we'll go ahead and just do another one. Why not? Because if we're going to have multiple examples on an assignment, we're going to see that. We say this is radical 3, then this is going to be radical 3 divided by radical 3 because we know it is a multiplication or division that gets us from one to the other, which means this would equal 1 and that would equal 2 and we would be good. And that goes back to just our original proof. Again, in our calculator, 7 times the square root of 3, which we can do. If we want the exact decimal, which makes more sense to me, is approximately equal to 12.1 to the nearest tenth. Let's make that a little cleaner to see. And we are looking at feet. So again, if you could check that with the Pythagorean theorem, if we wanted to, except we don't have lengths here to determine this other side. And so we can use this method to determine the information that we need based on the angles given. And that really wraps up our lesson. That is the most of what we're going to be covering today. I know it went a little longer than I planned, but I want to make sure that you have everything that you need. As always, you're welcome to skip around in the lessons or go back and pause to go over things that you need. But most importantly, practice the problems. Get to a place where you're really stumped and then ask for help so that we can go past it and help you understand this material. We're working in an online forum, which is not super easy to deal with, but I want you all to do well, so please ask the questions, take the time to make sure you understand the material, and we'll come back and start on the next section in a little bit.